Hello, this video introduces triple integrals in cylindrical coordinates. If you remember back to when we did double integrals, we found that sometimes it was easier to evaluate a double integral when we converted to polar coordinates. So this is a similar idea. Cylindrical coordinates are polar coordinates, but three-dimensionally. So two-dimensional polar coordinates, we have x and y, so that's rectangular, and we can convert that to r and theta. So we can express a point in x and y in terms of r and theta. Cylindrical is polar coordinates, but in 3D. We still have r and theta, but now we're also introducing z. So z in rectangular is the same as z in cylindrical. So in our two space in x and y, we have r and theta. So we're going to go some angle, we're going to go out for the radius, and then we're just going to go up. So z stays the same. First thing that we're going to have to do is we're going to have to be able to convert, of course. So a lot of these are the same as polar. X is going to be r cosine theta. Y is going to be r sine theta. And then, like we said, z just stays z. Now, if we're going to go to the reverse direction, if we have rectangular coordinates that we want to convert to cylindrical coordinates, r squared is going to be x squared add y squared, like before. Tangent of theta is y over x, and of course, z just stays z. So in this video, we're going to start with a little bit of the intro. Can we plot points? Can we convert points? Do we know what surfaces look like? And then we're going to talk about how do we take a triple integral in rectangular coordinates and evaluate instead in cylindrical coordinates. So let's start with example number 1, where we are going to plot a point in cylindrical and find the rectangular coordinates. Similar idea in B. Okay, so in A, plot 2, 2/3, 1. So this is our r, our theta, and our z. So if I draw myself my xy plane, or xyz plane, the first thing that I'm going to do is I'm going to move 2 pi over 3. So this is all on the xy plane, so it's a little hard to visualize it, but you're rotating 2 pi over 3 in the xy plane. Then we are moving out 2 units, and then we are moving up 1. So that is our point. So again, pretty hard to visualize, but we're going an angle on the xy plane, we're moving out 2, and then we are moving up 1. So then if we convert to rectangular, we have our x is equal to 2 cosine of 2 pi over 3, which is going to be -1. Our y is 2 sine of 2 pi over 3, which is going to be √3. And our z just stays z. So this same point can be expressed as -1, √3, 1. Now, just make sure that that makes sense. Does the point that we have plotted, does it make sense that it would have a negative x value, but positive y and z? Well, yes, that checks out. Okay, in B, let's go the reverse direction. We now have a point in rectangular coordinates that we want to convert to cylindrical. So we know that r squared is equal to x squared add y squared. So we get an r of 3√2. We're going to keep our r positive. We also know that tangent of theta is y over x, or -1. This is where people tend to mess up. Remember that tangent can be -1 in 2 places. That could mean that our tangent is 3 pi over 4 or 7 pi over 4. So that matters, and then z just stays z. So the question is, how do we determine what our value of theta is? Well, it depends on where the point is. So we have a positive x, negative y, negative z. So if you consider where that point is, we have to figure out how much did we rotate. How much did we rotate? If we consider just x and y, 4th quadrant, that would be 7 pi over 4. So the z doesn't come into play in this case. So same point in cylindrical coordinates then would be 3√2, 7 pi over 4, -7. So like I said, I have to stress, with theta, there's always going to be 2 possible options, and you have to pick the correct value based on the point in the figure. Okay, last thing that we're going to do before we move on is we are going to take a look at a surface. So we have this surface, z is equal to r. So if we think about what's happening, as z is getting bigger, the radius is also getting bigger. Now maybe you know what this looks like, the way that it's written. It might also be nice to write this in a form that is a little more friendly to us, which is z is equal to x squared plus y squared, or z squared is equal to x squared plus y squared. This would be a cone. So if we were to graph this, ooh, this is a little bit of a rough figure, sorry. This is our cone. Now, thinking back, is it both pieces? Can z be negative? Yes. Can r be negative? Also yes. So it's both pieces of these cones. So now that we've been introduced to cylindrical coordinates, which are new but not really, it's really just adding on to polar coordinates, we're going to talk about how are we going to evaluate triple integrals in cylindrical coordinates. So taking a look, if we recall, we have our triple integral of f of xyz dv, and we expressed that as a Riemann sum. And we said this delta v of k is just the area of the base multiplied by the height. So this gives us a volume, and then this is the value of the function. From earlier, and by earlier I mean an earlier video, we know that delta v of k is equal to r of k star, delta r of k, delta theta of k. So that came from 2D, from two-dimensional, and now three-dimensional, we have that height, right? So this is the 2D part, the area of the base, and then we have to multiply by the height. So what that becomes then is our triple integral is now going to become the triple integral of f of r theta z. When we convert to cylindrical, we get another r, and then we have dr d theta dz. So it's going to be very similar to what we did before. Remember, you're going to get an extra r. And then we have dr d theta dz. I will tell you, convention is to go dz dr d theta. So that is convention. Okay, and then you have this figure to the left that is explaining what we're doing. But ultimately, what you want to know is when you convert from rectangular to cylindrical, you're still going to get that extra r. Okay, finding the limits of integration. What you're going to do is you need to identify the upper surface. So z, you're going to express as a function of r and theta. And then your lower surface, z, is going to be a function of r and theta. And then, of course, you're going to make your projection onto the xy plane to determine the bounds. So I think this is going to make the most sense once we do an example. So I'm going to tell you this is a longer example. So as you can see down below, there is room on the next page for you to write some more. So let's give this one a try. Evaluate the triple integral of g dv, where g lies within x squared plus y squared equals 1, below z equals 4, and above z equals 1, subtract x squared, subtract y squared. So my first question for us is, what does this triple integral actually find? Well, any normal triple integral finds a hypervolume. But if we look at this one, this is 1 times dv. So what we are calculating is a volume. Triple integral of 1 dv is a volume, just like a double integral of 1 dA is an area. So we're looking for a volume. What's going to be helpful here, like it normally is to draw a figure. Okay, x squared plus y squared equals 1 is a cylinder, and we're looking at below z equals 4. So we're going to go up to z equals 4, and then we have our x squared plus y squared equals 1, so that's a circle with a radius of 1. So this is going to be a cylinder. Oops, it's a little too big. Okay, so here is our cylinder. So we've done the x squared plus y squared equals 1, we've done the z equals 4, but we haven't done this 1 subtract x squared subtract y squared. So that is a hemisphere, so that's the top half of a sphere. So not a great figure, so I'm going to put this into words. What this is this is a cylinder, and we are removing the bump at the bottom. Okay, so let's give this one a try. We're going to set up our volume. We have our triple integral of 1 dv. My z goes from that lower bound of 1 minus x squared minus y squared up to z equals 4. And then the rest of our figure is the projection on the xy plane, which is a circle down here, that x squared plus y squared equals 1. So if I decide to do y next, and then x, like we've seen many times, y goes from negative square root of 1 minus x squared to positive square root of 1 minus x squared, and x goes from negative 1 to 1. Similar to polar, anytime you see a circle like this indicates that cylindrical might be your better option. So what we're going to do is we're going to convert this to cylindrical. So we still have that 1. As soon as we convert to cylindrical, we have an r. And convention then is dz, dr, d theta. So now z is again going from this hemisphere up to z equals 4. The hemisphere, though, we're going to need to write in cylindrical. So our limits for z now are 1 subtract r squared up to 4. And now we're looking at that circle, so the circle that we had here. So my radius goes from 0 to 1, and then theta goes from 0 to 2 pi. Okay, and now we're ready to actually evaluate this. So what I'm going to do is I'm going to move this onto the next page for the evaluation part. So again, we have 0 to 2 pi, 0 to 1, 1 subtract r squared to 4 of r dz dr d theta. So this will give me 0 to 2 pi, 0 to 1 of r times z from z equals 1 subtract r squared to z equals 4. So doing a little simplifying, this will give me r multiplied by 4 subtract 1 minus r squared. And then we have dr d theta. So this then becomes 0 to 2 pi, 0 to 1, a 3r, add r cubed, dr d theta. So I get 0 to 2 pi. Once I integrate, this is going to be 3 over 2 r squared, add 1/4 r to the 4th from 0 to 1. So this then is 0 to 2 pi of 7 over 4 d theta. So finally, I get 7 over 4 times 2 pi. So that volume then is 7 over 2 pi. Okay, we got 2 more examples. So example number 4 says convert from rectangular to cylindrical. So this is an example that's in rectangular that looks pretty nasty. So we think cylindrical might be better. I'm going to start by converting this x squared plus y squared. So I'm still going to have my triple integral x squared plus y squared is r squared. As soon as I convert to cylindrical, I'm going to get another r, and then convention is dz dr d theta. Limits for z are from square root of x squared plus y squared to 2, so that'll be from r to 2. Now the trickiest part is figuring out the limits of integration for r and theta, so that's what we're going to look at here. And my suggestion is that you sketch r. Now in this case, you probably recognize that r is a circle with a radius of 2, and we're looking at the whole circle. So r is going to go from 0 to 2, and theta will go from 0 to 2 pi. Now, I think we can certainly agree that integrating this is significantly easier than integrating this. Now, that one was just for practice setting up. I'm not going to integrate it. If you want to integrate it, though, I'm going to tell you that you get an answer of 16 pi over 5. Okay, and you have a note here in pink at the bottom. You need to be able to recognize when rectangular coordinates are not the best option. So if you were given this original problem, I might not tell you to convert to cylindrical. You might need to recognize that converting to cylindrical is going to be a better option. That'll be on you. Okay, last example, and it's this example number 5. Let E be the region inside the sphere of radius 2 centered at the origin, and above the plane z equals 1. Find the volume of E. Okay, so first thing to remember is volume is the triple integral over our region dv. So our volume in this case, triple integral of 1. If I do this in cylindrical, which I am probably going to do because I have this sphere, I'm going to get my r, and then convention is dz, dr, d theta. And we are looking at the portion of the sphere above the plane z equals 1, which means that z is going from 1 to our sphere. So our equation of our sphere here is going to be x squared add y squared add z squared equals 4. So then we get z squared is equal to 4 subtract x squared subtract y squared, or 4 subtract r squared, which means that z is going up to 4 subtract r squared, or the square root of that. Now that we figured out the limits for z, we have to figure out the limits for r and theta, or x and y. And those happen where these two figures intersect. So that would be our projection, our d. So we have x squared add y squared add z squared equals 4. We also have the figure z equals 1, which means that our region d is x squared add y squared equals 3. So our radius is going to go from 0 to root 3, and then theta will go from 0 to 2 pi. And again, we're not going to evaluate this one. We've done a lot of evaluating. The biggest thing I want to practice is setting it up. Okay, so in this video, what we talked about, we introduced cylindrical coordinates, which are very similar to polar, but we're looking in 3D. Big thing is when you switch to cylindrical, you need to remember that r, and of course you need to know when cylindrical is the best option. Now, next video, we're going to learn one more coordinate system for evaluating triple integrals. So then you'll know rectangular, you'll know cylindrical, and then the last one is called spherical. So see you in the next video.